Okay, so in the first part of this talk, I mentioned these two stories. This thing having to do with dt of a Calabi-Yau threefold. We have these dt invariant, and there's a wall crossing for them that depend upon variation of the stability parameter. In the physics language, it has to do with some 4D BPS states, so the 4D theory defined from string theory on your Calabi-Yau 3. And then there is this other story which is about some kind of Landau-Ginzburg model. And here you have this, what I call μij, this kind of gradient flow lines. Which also have a wall crossing story when you vary W. And in physics context, they have to do with 2D BPS states, where the 2D theory is like a sigma model with targets is space with a function. And kind of the original question I had is, can you realize this story as a special case of C story? So if I have my Calabi-Yau 3, and I count either Cauchy or special Lagrangian as this dt invariance, the goal is, can I find some space M with an holomorphic function W, so is that the dt invariants become count of gradient flow lines between critical points. And so that the wall crossing here becomes the wall crossing here. So on the face of it, maybe it just looks different. Here we're thinking typically of situation having finitely many critical points. So here I get, here the invariants are indexed by this pair of critical points. Where here I have infinitely many invariants indexed by some kind of class in some lattice. But of course, you might say, okay, maybe you should not assume there's finitely many critical points. Maybe W might have infinitely many critical points. And actually, you might do that, but I claim that just doing that will not be enough to find that. What we will really need to do is to really extend the class of MW we allow, and in particular, we'll need to allow M to be infinite dimensional. So the main point will be to find C story from C story by taking M to be infinite dimensional. And the claim is that there is a natural source of infinite dimensional spaces with holomorphic functions, which are given by space of paths between holomorphic Lagrangians in holomorphic symplectic manifolds. So here it's where we start talking about holomorphic Floer theory, which is something of completely independent interest. You might not care about dt invariance at all. It's just something extremely natural. If you think of a usual Floer theory of symplectic manifold as coming from doing Morse theory on the space of paths connecting Lagrangians, you might try to do the same thing in the complex setting. So I will consider, okay, so now my notation will all be, I will denote by P some holomorphic symplectic manifold. So it's a complex manifold. So I have a distinguished complex structure I, and I have a holomorphic symplectic form by omega I. So it's non-degenerate holomorphic 2 form. And so it's like some holomorphic or complex analog of a symplectic, of a real symplectic manifold. And in such a thing, we can look at holomorphic Lagrangian submanifolds. So L inside P is holomorphic Lagrangian. So if it's a complex submanifold, and omega restricted to L, okay, I call it omega I restricted to L is equal to 0. And now in ordinary Floer theory, you look at Okay, in the simplest case, you look at pairs of Lagrangians. Here is L. Here is L prime. So now we look at a pair of holomorphic Lagrangians and manifold. And something which is, if you want to do an analog of flow theory at some kind of heuristic way, you might want to look at the collection of paths between these two L and L prime. So you might want to consider the space of paths between L, L prime. So this thing will be some kind of infinite-dimensional manifold. And the claim is that on this infinite-dimensional manifold, there is a natural function. Maybe more precisely on the universal cover of that, there will be a natural function. So I take the universal cover, I take a base point. So maybe here is some base path. Maybe I call it P0, this is a base path. And then if I have another point in this space P, so a point in the universal cover, it's a path connecting my base point to my point. So it's a path of paths inside this space. So it's some kind of a surface here that I denote by S, maybe P0. And then if I have a surface, I can just integrate the symplectic form. I can just look at the symplectic error of this surface. Just integrate omega on this surface. So that's P2. Another way to say it, you can say if omega I is exact, it will be D of a one form. And you might just integrate this one form on such a path. But of course, maybe globally there is no one form. So which is why you need to go to this universal cover. And if you do that for a usual real symplectic manifold, everything is real, you get a real function, real valued function. And then if you do usual Morse theory for this real valued function, you get the critical points are related to intersection points of the Lagrangians. And gradient flow lines have to do with holomorphic curves for a compatible, almost complex structure. And this thing gives you the standard structure in flow theory. But now you have a complex valued function. And so you can do complex Morse theory. So we can do everything we discussed here for this space and this function, but in this context of this space and this function. So I think here it's underlying to the claim that space is infinite-dimensional space because it is a complex structure to start with, as a natural structure of infinite-dimensional complex manifold. And this function is like holomorphic on this infinite-dimensional complex manifold. And so you can view that as some kind of Landau-Giersprung model, but for some infinite-dimensional space. So now you can just run the story we reviewed previously. So we discussed that in this context, there are a number of interesting things you can do. So first of all, you can look at the critical points of that, which are, again, intersection points between the Lagrangians. And then there will be these, so this thing will be my critical point. So what I was labeled by ij before. In this context now, they become intersection points between my two Lagrangians. And now if you think about what is mu ij, so there's a question, so what are these mu ij? So there are gradient flow lines between critical points in this space of paths. And so it's like, in usual flow theory, the gradient flow line of the action function will give you holomorphic curves. So here the same, this mu ij will be count of holomorphic curves. Except here, to get this gradient flow line, I have to tune this zeta parameter. I have to tune it to this zeta equals zeta ij. And this tuning here corresponds to a tuning of the complex structure. So here, when I say holomorphic curve, it's crucial as it's not holomorphic with respect to the original complex structure. Like in usual flow theory, there is no complex structure to start with, but you pick a compatible complex structure with a symplectic structure. So here, the analog of making some choice of compatible almost complex structure is choosing some auxiliary j and k, so that I, j, k form some quaternionic triple, or maybe like almost quaternionic triple of complex structures. And then if you go through what does it mean to have a gradient flow line for zeta ij, for real part of this function over zeta, you will find that you find holomorphic curve for the complex structure j zeta ij, where j zeta ij is like linear combination of j and k. So you should really think you're in some kind of hyperkähler situation. There is a twistor sphere. There is a S2 of compatible complex structure made of this ijk. There is a distinguished one, which is the one we start with, which defines the holomorphic form we care about. And then there is some circle of linear combination of j and k with real coefficients, which is some kind of like orthogonal to this point. And what we were discussing before, these choices of phase, is related to the choice of point on the circle. And here, for a given ij, essentially the tuning is like the zeta ij. It has to be the kind of the correct thing. It has to be the phase of this complex number, like integrate over this kind of surfaces, something like that. Okay, so here the same way, so as in the finite dimensional picture, if you're in this kind of hyperkähler type situation, if you consider, and like other thing I should say, which kind of explain why this story makes sense. So these things are like holomorphic Lagrangians, so capital omega I respect to that is 0. But if you take a complex structure on this circle, and if you look at the corresponding Kähler or symplectic form, then this symplectic form is 0 on your Lagrangian, so your Lagrangian is the ordinary Lagrangian for this ordinary symplectic form, and so this count of holomorphic curve is a usual count of holomorphic curve with boundary on like a usual Lagrangian. Okay. And the claim is that for a random complex structure on this circle, there will be no such a curve. But if you tune correctly the point on this curve, you will get some, and you get a version of this curve. And something else I need to be, which is crucially important, which is here, it's actually really needed to take a universal cover. Which is like in usual first theory, you have Novikov parameters, which come from this universal cover. And so correspondingly here, you will have things like Novikov parameters. So essentially like the pi1, like roughly the pi1 of this space of paths. Okay. Okay, I will not. Okay. It has to do with some kind of, okay, if I had a single Lagrangian, it has to do with some kind of relative H2 of your manifold relatively to L. And which will translate in the fact that for intersection point I, actually you don't have a single critical point of this functional, but like infinitely many of them indexed by some kind of relative H2. I will be more concrete about that in a concrete example later.
Do you expect there to be the same number of holomorphic curves of all of the different?
Yeah, so the claim that some of this special value you should look at is kind of fixed by the geometry.
Okay.
So if you look at two specific intersection points, there's a particular complex structure which you should look at. And again, the correct lift to the universal cover, whatever. Like the kind of correct choice of this surface tell you what is the phase of this number, tell you the right complex structure to look at. In the same way that in finite dimension, you have the two critical points, so the kind of difference between the critical values of the function tell you what is the phase to look at.
So if you have a holomorphic, so this is like a holomorphic symplectic case, I say like this.
Yes.
IJK.
Yes, that's right, exactly. So which is his picture? Yeah, IJK.
So
Yeah.
in some of the example, then only I and minus I is not R phi, and all the other are R phi.
Yeah, exactly. Like for example, like Itchin system, for example, type. Yeah, that's right.
So all the other has you have one function from one of the others, then the same function for everybody except 0 and infinity.
Yeah,
all the other alpha, right? So
yeah.
Function.
Yeah.
Exactly the same amount, right?
Yeah, that's right.
So
yes.
therefore, all of them can do this except the 0 and infinity. So you're supposed to capture those information as 0 and infinity when they lost the function.
Yeah, so I think in principle you can try to run the story for any I. So you can decide what you call I, so there should be some story.
Yeah,
but I don't. Yeah, that's right. So I don't know if you've. Yeah, that's right. So yeah, so I don't know. So the answer I will consider will be exactly of this type. The kind of typical example we consider will be of this type, but we'll consider the kind of nice situation where the I is a 1, where not the other. But indeed, like yeah. So for example, like from a 3D mirror symmetry perspective, where all the IJK should be, I mean, they're all as good. And you should look at all of them. But yeah, that's why I don't know what we do if you look specifically to.
Yeah, no, but it's interesting.
Yeah, definitely it is interesting. I agree. Okay. Okay, so at this point, this thing is not so different from usual first theory. You just get this holomorphic curves. Except so in first series, this count of holomorphic curves give you some differential to cook up a Floer complex. But here, everything lives at one categorical level up, because we not only have this count of gradient flow line, but you also have this count of solutions to this instanton equation. Which are like roughly like perturbed holomorphic curve inside this space of paths. And so a holomorphic curve in the space of paths in the original manifold will be some kind of three-dimensional thing. So we'll get some 3D things. And you should think carefully about how to phrase boundary conditions mapping to your space P. So it's like U, maybe like XST. And again, and I will not look at the precise equation. So roughly what you get is some version of something called the future equation, which is something of the form some PD equation looking like that. So if your thing is like independent of t, then it will be a soliton. It will be some version of some holomorphic curve equation. And it's something which incorporates every IJK. And pretty simple, you also need to tune the zeta. So it's not exactly IJK, but the correct tuning. And so you might believe that you should be able to count that, maybe. And then if you would be able to count that, it will mean you will get some kind of vector spaces or complexes attached to a pair of critical points. And as we discussed, out of this data, in the finite dimensional situation, you might hope to get at the end of the day a category, which will be some kind of Fukaya-saddle category of this kind of function on this infinite dimensional space, so some kind of Fukaya category of this W. And this thing should be some kind of category like attached to a pair of Lagrangian L and L prime. So in usual first theory, to a pair of Lagrangian L L prime, you attach a group, like the Floer cohomology group. And it's this kind of complex setup. Everything is one category level up. And so you might hope to attach some kind of category to this pair of Lagrangians. And yeah.
So when one level down,
yeah.
The reason that holomorphic curves define some differential in floor theory is that they degenerate in some relatively limited ways. Is there some expectation that these three-dimensional objects degenerate in some?
So obviously, to make any of that precise, there will be intra-mini analytic issues, and the main issues in it is the kind of bubbling behavior of these kind of equations. So let me mention that so there is some work by Doan and Retchikov, who also took as starting point this kind of formal picture, and but they started to think more seriously about the analytic problems. And so definitely they do like the first step in this direction, but certainly it's not understood yet what happens in general. In particular, there could be some, and I think in general there are some known bad bubbling behavior of this footer equation, and I think it's unclear how much they messed up with a naive expectation or not.
I guess maybe we can ask Retchikov.
Yeah, that's why you should ask next week. I'm pretty sure at some point I ask. Yeah, I think there is a concrete thing which is known about some kind of bad bubbling of this equation, and it's an obvious thing which maybe makes this story undefined or problematic. Yes.
In previous case, you look at the polygon.
Yes.
And that is the data of the category. So what's the domain?
Yeah, that's also one is to think. So naively, if it's really some kind of polygon mapping to this space of paths, I mean, the most naive thing to say is this path is really a map from 0, 1 to, so it's like a polygon times 0, 1 or something, like the most naive. And of course, the kind of issue is, does the bubbling kind of preserve this product structure? Probably not, which is kind of the issue. Okay. So, but yeah. So this thing is like expectation. So the only thing which is like slightly better than saying consider the Foucault-Seidel category is that at least we don't talk about infinite-dimensional Lagrangian, which would be maybe really without hope. So here the thing is like slightly more approachable. There is a concrete equations, like finite-dimensional type equation, and but then you have to understand kind of bubbling of compactness issue for this PDE, which is maybe slightly better. And so, of course, if you just follow a formal analogy, so the conclusion is that for any LNL prime, you get a category. In the usual case, for any LNL prime, you get some kind of group, which then, when you consider all possible Lagrangians, becomes some morphism in the Foucault category. Here, you can expect this kind of category to be some kind of home space in some kind of 2 category. So, some kind of maybe in this paper, maybe it's referred to footer category of our holomorphic symplectic manifolds or some kind of. Okay, so the kind of just prediction of this formal picture is that if you run this kind of Foucault-Seidel story for pair of Lagrangian, you should get some kind of, and this thing is a version of first series, so it's a kind of A model type version of some 2 category attached to a holomorphic symplectic manifold. And maybe as a side note, so there is a story which was maybe better known, which is if you have a holomorphic symplectic manifold, instead of doing this A model story, you can do a B model story. You can try to look at, instead of Foucault-Seidel story, you can try to look at category of matrix factorizations. And then what you get is this thing called this Rosonsky-Witten. And there's a two category coming from Rosonsky-Witten theory, which is some kind of B-model category attached to your holomorphic symplectic manifold. And all of these categories should be relevant if you ultimately care about something like a 3D mirror symmetry. So this is a holomorphic symplectic manifold. And so a common source thing is obviously 3D, because the usual Landau-Ginzburg model story, it's like a 2D story, but here's a 2D story in the space of paths. So in other words, here there is some kind of, we are really looking at some kind of theory of maps from this is a holomorphic symplectic manifold. And then what we're really doing is, when we do consider this pair of Lagrangians, we are looking at R2 times the interval, which is our path, and then we put boundary condition on this interval. And the claim is that effectively what you get is a 2D theory, but it's a 2D theory valued in the space of paths. Like equipped with this function. Okay, so there will be some three-dimensional theory. When you reduce it on an interval, determined by this Lagrangian, this is two-dimensional theory. And then these categories are the kind of categories of boundary conditions of this two-dimensional thing. And these two categories are the category of boundary condition of this three-dimensional theory. So now I will just finish by, so this thing is vague enough so that the next proposal will be even more vague, which is to run, okay, so at the end I want, okay, so the claim is that this story involving holomorphic symplectic manifold in some ways it's like a source of example of Landau-Ginzburg model. I have this space of paths with holomorphic function. And now the question I'm going to ask is, if I come back to my DT setup with a Calabi-Yau 3 in my geometric DT invariant, maybe I can find some holomorphic symplectic manifold and some pair of Lagrangians, so that if I look at this infinite-dimensional space of paths and this holomorphic function on it, then running this theory for that will recover me the DT invariants. So as I mentioned, you might care about this story from many different perspectives. Like if you just get about 3D mirror symmetries, this kind of thing should be something very relevant. But I will say nothing about that, and I will only talk about the original story, which has to do with DT invariants, and which in some sense is closer to 4D than 3D. Okay, so I come back to my DT invariants. So somehow out of my DT story, I want to have some holomorphic symplectic or hyperkähler space. And in general, I don't know how to produce that. So I guess we'll know roughly what is the answer if I focus on the A side of X. So I look at the Fukaya category of X. So then what I will denote it by B is something like some kind of complex moduli space of moduli of X.
X is Calabi-Yau 3?
Yeah, X Calabi-Yau 3. Yeah. And then, so I have my space B. And now over this space B, there is a natural space.
So you want to be the space of omega?
Yeah, that's right. So it's like, okay, so there is this difference between complex and like, yeah, versus, okay, this space omega. And here there is some subtlety having to do with scaling omega, or the class of omega, which is a subtlety which is responsible why sometimes I'm confused about compact versus non-compact. So I think the kind of class of example where I'm more confident into what I will be talking about is when X is non-compact. So like omega does not have a cohomology class, so we cannot really rescale omega. And in the compact situation, we need to think more carefully. And I would be happy to discuss that. Okay, so over this space, so if you take a point in this space, you have a X is like a Calabi-Yau with a particular complex structure. In particular, on your middle cohomology, you have some Hodge structure. So your H3. As a Hodge decomposition. And each time you have this kind of odd degree type Hodge decomposition, there will be a corresponding intermediate Jacobian. So maybe I denote by G. P is the corresponding intermediate in which, so I will always get confused. Someone can correct me. You take the correct half of this decomposition, and you divide by the Z cohomology. So maybe I will let you guess the correct. You need to remember in which direction is the Hodge filtration going.
So the base is the other two directions.
Right?
Yeah, base is the other two. So the base is H3 0 and H3 1.
Okay, so base is H3 0 and H2 1. So it should be H1. Thank you. Okay, so you get this torus. And I can look at you as a kind of universal family of this torus, tori, and the claim is that I get a space which will be by P. So P over B. And so the claim that, so B is like complex, it's like the moduli space of complex structures. And the claim that this P is like naturally a hyperkähler.
Is it true for high law compact?
So, sorry for?
Law compact X is also true.
So I think I would need to think about, what is the correct definition of non-compact Calabi-Yau. But for example, there's a large class of non-compact Calabi-Yau threefold for which the answer is naturally the moduli space of fixed bundle. So each in system for which is certainly hyperkähler. So I'm pretty sure there's some paper by Donaghy et al. Which should consider some non-compact Calabi-Yau with correct assumption, but I'm not fully sure actually. So yeah, because of course it cannot be saying something is something is a bit of a bad definition. So, but anyway, so for example,
if you replace X by Calabi-Yau free category, then you should get what, only a joint structure. If you X is only Calabi-Yau free category.
so okay, so let me see. So this thing is a space of stability conditions, and so I think I will still ideally I would still like to get the same. And yeah, so this joint structure story is some kind of purely I don't. It's kind of purely holomorphic version of hyperkähler. It's like this complex hyperkähler, like everything is holomorphic. But there should also be a story like that. It's just the purely holomorphic story is maybe like easier to work with as a first step. But like the kind of Riemann-Hilbert problem that Bridger considered, which would produce this joint structure type of thing. There's a version of them considered by Gayoti-Moyniaski in the physics literature, whose output should be something like hyperkähler type structure. So here, if I want to say something concrete, there are some specific non-compact Calabi-Yau 3, where this geometry is just a well-known story, just the moduli space of fixed bundle, and this thing is each in fibration. This thing is a perfectly well-defined geometry. And now, okay, so I have my hyperkähler space, and now I would like to find two Lagrangians, such that somehow if I run the kind of 2D story for these two Lagrangian. I want something having to do with my DT invariance. Okay, so my Lagrangian should depend on the position of my base point. So there is an obvious choice of holomorphic Lagrangian, which is a fiber. Okay, so it's another claim that this vibration is kind of a holomorphic Lagrangian with respect to the. So there is a natural complex structure I in which this vibration is holomorphic. And then the fiber, so the fiber FB will be a holomorphic Lagrangian. And then for the other one, I would just take something boring. And maybe it's possible to rephrase the story without mentioning the second one, but I just find it easier to mention the second one, is to take a section. Okay, so here is some kind of section. And maybe there is a question in general, is there always a section? Maybe it's, okay, so I will take S. Some holomorphic section. So for example, in the X bundle story, I know there is a preferred section. I mean, there is a section. There is this thing called the itching section, for example. And in general, it's maybe a question: is there always a natural choice for a section? And so. But anyway, so I assume that maybe it's reasonable in this torus vibration structure that only in some cases there will be something like a section. And then I want to run the story for these two Lagrangians. So I want to look at, okay, so this kind of fiber and this kind of section. And so maybe at the beginning it looks confusing because you think of the fiber and a section, so I have only one intersection point. So maybe it looks boring. It looks like my functional on my space of paths, so you think in my infinite dimensional space of paths. It looks like, okay, maybe there's only one critical point, which sounds really boring and confusing. But the whole point, okay, the kind of whole point of the story that is fiber, HB, is non-simply connected, essentially because you quotiented by this H3XZ, so this is lattice, which makes the fibers non-simply connected. And this lattice will make your space of paths non-simply connected. So it's essential to go to the universal cover. And roughly, okay, and up to skipping details, I would claim that roughly, so it's not what I'm saying, it's not fully true, but in first approximation, the fundamental group of the space of paths is like exactly this H3XZ. So roughly, like what you need to calculate is some kind of maybe a relative H2 of your space relatively to. Okay. And this thing has a map to H1 of FB, which is like H3 XZ. So maybe there might be something else, but in first approximation, you get this group, which means that on the universal cover, you get a lattice worth of critical points, which are, so if you fix a reference one, then they are naturally indexed by gamma inside this H3 XZ, which is exactly what we want in DT theory. If you want to do DT theory for the Fukaya category, we try to count Lagrangians which have class in H3 XZ. So now I have a kind of natural function which has like infinitely critical points, which are like naturally indexed by this H3 XZ. And so now is a kind of obvious guess or conjecture, or like the conjecture. So now the conjecture. So there are like various versions of the conjecture, but maybe the first one is omega gamma of B. So should be what I want, meaning it should be a count of gradient flow lines in this infinite dimensional space. So count here. But then this path will become some as we discussed before, will become essentially some holomorphic curve in this geometry. So this thing should be equal to some count of j zeta holomorphic curves in P. And if you go through all the analogies and expectations, the correct zeta to pick is like the phase of the center charge gamma, which is like the phase of the period of the integral of omega on gamma. So if you look at the particular gamma, there's a particular period of omega on this gamma, which is a complex number. And then you look at this phase, tell you which complex structure to look at in this geometry. And then you want to look at the curve in this geometry with boundary on these two Lagrangians. And the claim is that in many situations, so you get some, like, I think in many situations, I claim this curve, what it will look like at the end, it will look like a disk with boundary on FB. And maybe an intersecting a point corresponding to the intersection with a zero section. So this kind of holomorphic disks. And maybe some remark is that this kind of holomorphic disks are exactly the kind of holomorphic disk which will appear if we try to do SYZ mirror symmetry for this family with respect to a complex structure.
When you map downstairs, B is like a Hitchin base, right?
Yeah, that's right, exactly, yeah.
Then why is the maximum principle?
But the key point is that they are singular fibers.
Oh, okay.
So they are singular fibers.
What is singular fiber? They're all torus. Unless you go to the infinity.
Okay. So I'm cheating. So B is not the honest complex moduli. It's like the complex moduli you will add the discriminant locus.
It's like Hitchin vibration.
Which is like Hitchin vibration. So it's essential for this story to add in the thing. Again, maybe from a purely incomplete generality, maybe it's unclear what to add or how to. So yes, yeah, so it's indeed essential. Indeed, the origin of this thing will be the singular fibers. Okay. And so this thing is a conjecture at the numerical level, and maybe if you are more ambitious, you can ask maybe at the categorical level, you get more and so on. And I would just finish by mentioning that actually there are many like rigorous results which can be interpreted as a statement of this form. I'm saying some DT invariants of some Calabi-Yau 3 are equal to some honestly defined count of holomorphic curves. So maybe not curve with boundary, but maybe some algebra geometric approximation of that, like log Gromov-Witten type invariants. So for example, with Julia, we have a paper which is telling that if you look at DT invariants of some quiver with potential, so some kind of representation theoretic, not geometric starting point, you look at the DT invariants. Then under some assumption, these DT invariants will be equal to some general 0 log Gromov-Witten invariants of the corresponding cluster variety, which is some kind of natural holomorphic symplectic variety attached to the quiver. And the proof of this correspondence is kind of non-trivially geometric. It's saying that both of them are controlled by the same scattering diagram, where here the scattering diagram has to do with the Walk-Crossing behavior, where here the Walk-Crossing in DT theory, where here the Walk-Crossing diagram has to do with like mirror symmetry or tropical curves. It's just a kind of miracle that they agree. And this conjecture or this picture is supposed to be a heuristic picture, which is some kind of like more conceptual explanation or maybe something which will apply in more interesting geometric context or why this statement should be true. So I claim there are like many precise mathematical statements which are of this form. And this conjecture is some kind of like big picture heuristic reason for why it should be true. And maybe I just end by one word, which is like the maybe like physics picture, which is kind of obvious. So we started in 10D, we went on our Calabi-Yau 3, we went to 4D. And then in physics language, the way these space appear is that if you put your 4D theory on R3 times a circle, it's expected that theory living on R3 is a sigma model valued in this guy. So, and so you might just believe that if you look at the BPS particles here, you might ask, how are they described in terms of this sigma model? And you can reasonably argue that they will be described that way, which would be some kind of explanation.
The 10D field is a gravity field. You're just changing the complex structure.
Sorry?
The 10D field is the gravity field. It's just changing the...
Yeah, that's, I mean, the 10D is really like, it's really type 2 string theory. Yeah, that's right, which is the gravity, yeah. So somehow it's like one way to arrive at this kind of 3D. It's like one way to arrive at 3D, and the other way to arrive at 3D is what we discussed, starting with flow theory or 2D mirror symmetry, and just try to go one level up from going from real to complex. And so there are like two different ways to arrive to 3D, which like should be compatible. And yeah, I will just stop there. Thank you.
So that means that whenever you see those invariant or trivial invariant, that means that you have some infinity of the complex structure. Otherwise, then you will never...
Yes, that's right. Yeah, and so there's a question how much you can make this picture precise. So if we try to think geometrically what it means, I don't fully know what, but in this context here you are looking at special Lagrangian at this point. And if you move the complex structure, you might try to follow your special Lagrangian and see what happens to it. And maybe at some point your special Lagrangian will break into two other special Lagrangians. And maybe at some point it will break into something very special, like a Lagrangian 3-sphere. And this Lagrangian 3-sphere will collapse to a point and you will get a singularity, like a conical point in your Calabi-Yau. So this thing is like the simplest, so like kind of the simplest connection between the existence of special Lagrangian and the existence of singular fiber is to look at the situation like of a conical point. Your Calabi-Yau get a nodal point. There is a corresponding like vanishing cycle Lagrangian S3. Like the existence of this Lagrangian S3 is related to the fact that if I collapse it, there is a singularity in the complex moduli space.
But that's the collapse is controlled by homologous. I mean, because
the collapse
is the volume of the special Lagrangian is the topological data, right? So it's dictated by the period. If you collapse the class, I mean, that is exactly where the class vanished.
Yeah, exactly. So, which indeed, like, I mean, so these periods are some kind of coordinates on the complex moduli. And so exactly, there might be one of these periods going to 0. And so exactly the Lagrangian collapse. And actually, so there are examples. So for example, if you start with local P2 and look at the mirror of local P2, then you have this picture. And we know what the space B is. It's like the stringy Kerr-Modi space of local P2 or complex moduli on the mirror. And we know that there is like a single conical point. And I claim that in this case, everything will come from this conical point. So again, I don't know how to prove a statement about special Lagrangians, but actually I know a hypercally rotated version of this statement. So I know a statement about holomorphic curves, that they are captured by some scattering diagram. And this scattering diagram kind of originates entirely. So actually there is maybe on some cover, there are really 3 singularities which create the scattering diagrams that probably Michel will talk about tomorrow. And so everything is created by these singularities. So all possible holomorphic curve is created by these singularities. And this thing should mean that in this geometry, essentially all special Lagrangian, if you tune omega, they will all be made. So at some point, there will be some kind of wall. They will break into pieces. And at the end of the day, they are all made of this kind of basic Lagrangian 3-sphere, which collapse at the
image of that
singular point.
Be a graph?
Yeah, so I think if you take the kind of correct tropical limit, then you should get some kind of graph or tree, yeah.
There's no limit, no more limit you can take, no choice.
Sorry?
What tropical limit?
Yeah, I mean, I guess insights is, yeah, one needs to think. So it's like in the same as in, yeah, so what do you need for XYZ? You need, okay, let me see.
You choose a scalar form, you choose a scalar class. If there's a model of complex, you choose a scalar class.
Yeah, so, okay. I will need to think about, so in the physics story, it's like the radius of this S1. And then I will need to think when I go through the correspondence way, the radius of the S1. But it's really when when R is really small, so it's kind of, so this thing is like some 3D Coulomb branch. Should become very close to this 4D Coulomb branch. So this thing should be very small, and I should get this graph. But yeah, indeed, one need to go through to see where is this parameter. Yeah.
So you had mentioned cluster algebras at the beginning.
Yes.
And, right, there's sort of a suggestion in physics literature that cluster algebras should be showing up in these 4D theories.
Yeah, that's right.
From the line operators. So that sort of
Oh, yeah, that's so indeed, these kind of spaces, they're really like Coulomb branch of these 4D theories. So with respect to the correct complex structures, so for this J and K, not for I, but for this J and K, often they will be cluster-like. And as mentioned, often they will be type of affine, and so the algebra function, yeah, essentially the cluster algebra, should be from this physics point of view, the line operators. And so you might ask, what is that in this picture? And so there is a confusing story that these spaces are kind of often like look like self-mirror. So they are not exactly okay. So I think the easiest way to make the connection is to look at the cluster algebra for the mirror, so function on the mirror. Under homological mirror symmetry, the function on the mirror is typically okay. So it's like home of the O to itself, just algebra function. And under homological mirror symmetry, this guy will go to the section on the mirror side. So this thing is like, so in usual homological mirror symmetry, this thing is kind of self-home in a Fukaya category between the section and itself. And in this cluster example, this thing is really non-compact, so this thing should really be interpreted in some kind of wrapped Fukaya sense. And when this thing got wrapped to get displaced from itself, there will be this intersection point, which will index some kind of basis of the space. And the naive expectation is that you get things like this canonical basis should come from this kind of intersection points. And what this Floer theoretic, holomorphic Floer theory picture suggests is something which probably is expected from other reason in representation theory, is that maybe this thing should be categorified. Maybe the cluster algebra should admit some kind of categorification. And the kind of one of these conjecture will be that if you do home between this guy and itself in this two categorical version of this Fukaya category, you should get a category, which is a categorification of the algebra of line operators. And there should be something more, which I think is not really, which is these things, there should be some kind of map or maybe action or home. Okay, so there will be more to be said. So of course, it's a cluster algebra, so there are charts. So if you have an element in the cluster algebra, you can read it in a given chart. And this kind of operation should have some meaning, like choosing a point here should be related to choosing a particular chart. And then, and so everything should interact. So in particular, the numbers which appear here, this dt invariance or this holomorphic curve, should be the same thing which appear in the scattering diagrams for cluster algebras considered by Grosek and Kontsevich. So actually, it is a setup in which we prove a mathematical result that if you look at this scattering diagram studied by Grosek and Kontsevich to study cluster algebras, often the corresponding number has some interpretation of dt of the quiver, but on the other hand, the corresponding number has some interpretation as 0 log Gromov Wheater invariance. So yeah. Yeah, so maybe from the point of view of system, maybe the most interesting part maybe like if there is ever some two-categorical holomorphic Floer series story, it should produce in particular some categorification of this line operator, and maybe from representation theory you have already some candidate for that from other reasons, and then it's like a prediction for what this two-categorical Floer theory should produce. And I think it would be extremely interesting to test it on any non-trivial case if it makes sense or not.
So if you started with a real tree manifold, then you were counting flat connections on it, which is a Heegard splitting,
yeah.
real tree manifold, and then you get a real symplectic manifold with two Lagrangians in it. I don't know, there's something like, on the one hand, that seems superficially similar to what you explained, but it isn't.
No, I mean,
naively.
I mean, definitely you can run the same. So this usual story is like how to relate some accounting on some three manifold to some Floer theory question, like intersection of two Lagrangian in a moduli space. And which is yeah, that's right. So you might ask, for example, if is there some kind of explanation for this type of conjectures by such kind of arguments. Maybe you start with something and then you do something and then you understand geometrically the meaning of these two Lagrangians, and yeah, and I don't know. So certainly there's some kind of obvious analog of the Atiyah-Floer conjecture, like instead of starting with a threefold, you start with a Calabi-Yau threefold. And then instead of having some Heegard splitting, maybe you consider degeneration of this Calabi-Yau to maybe like two Fano meeting a K3 surface. And then, yeah, and then there's the moduli space of sheaves here should be related to intersection of now complex Lagrangians in the moduli space of sheaves on K3. And then you can write towards this, apply this holomorphic Floer theory for this holomorphic Lagrangian in the moduli space of sheaves on K3. And this thing, and the natural obvious analog of Atiyah-Floer is that what you get here should be the same as what you get by doing something else here. So there is some kind of maybe obvious analog. Maybe this obvious analog is maybe not the most interesting from this point of view of this story, maybe.
So in that case, the symplectic structure is on the moduli space of object, or moduli space of quantum.
Yeah, that's also, which might be confusing. So yeah, so here in particular, like in this story, yeah, like the gamma is kind of fixed.
Right.
And then there is a story, which is maybe very confusing because this thing will produce. So we discussed that this is omega. Maybe there is a vector space, and maybe there is a vector space. There is a category. And so this category should be the category which in the moduli space of sheaves on K3. So in the moduli space of sheaves on K3, I have the Lagrangian of sheaves extending on one side, sheaves extending on the other side. And by this holomorphic Floer theory business, to this pair of Lagrangians, there should be a category attached to it. And this category, and so the version of Atiyah-Floer is that this category agrees with this category. But in my story, I never discussed this category. So the fact that in DT there is some higher category is maybe confusing from this point of view. But that's okay. Maybe it's something to think about it later. Yeah, that's so this thing is like another example of some like very interesting sounding statement. Like if you have some candidate for what is its category called DT invariant, it will give you some kind of prediction for what is the category attached to this pair of Lagrangian in this holomorphic symplectic moduli space.